Welcome to the E6 seminar today. Today we have with us Dr. Matthews Panteli. Hopefully I said the name properly. Dr. Panteli will be talking to us about towards resilient power systems, experiences and application from international projects. Dr. Panteli holds an assistant professor position within the Department of Electrical and Computer Engineering at University of Cyprus since January 2021 and an honorary lecturer position at the Department of Electrical and Electronic Engineering at Imperial College London since September 2022. Prior to joining University of Cyprus, he was a lecturer at Power and Energy Division of the University of Manchester, serving as the deputy lead of the Sustainable Energy Systems Research Cluster. His main research interests include techno-economic reliability, resiliency, and flexibility assessment of future low-carbon energy systems, grid integration of renewable energy sources, and integrated modeling and analysis of codependent critical infrastructure, in which he has successfully developed a multi-million research portfolio, attracting funding from research councils, industry, and European Commission. Matters is an IEEE senior member, an IET chartered engineer, the chair of CIGRE working group C4.47 on power systems resiliency, and CIGRE Cyprus National Committee, an invited member of multiple IEEE, CIGRE, and SIRED working groups, and also a fellow of Higher Education Academy. He serves as an associate editor of IEEE Transaction on Sustainable Energy and IET Renewable Power Generation. He is also the recipient of prestigious 2018 Newton Prize, and he was selected in the top 12 innovator for 2022 by the Innovation Radar Prize competition in European Commission. So let's welcome Dr. Panteli for today's talk. Matthias, back to you.
Thank you. Thank you very much, Anamika, and thank you for the invitation. I'm really excited to be able to share some views with you on the different projects that we did in the past 10 years or so. So the point of the presentation today, everybody, is to give you, in a nutshell, let's say, what we did in the different projects, and then I will be very happy to follow up with any discussions in case you found some pieces of the presentation interesting to follow up with more details. So, I mean, this is just an overview of our path, if you like, in the topic of power system resilience in terms of different projects that we completed successfully or currently running. So we started working on this topic from 2011, where basically we had the first project on resilience in UK called Resilient Electricity Networks for Great Britain. Then we got a project in collaboration with the colleagues from Chile, looking at disaster management resilience, in particular when it comes to earthquakes, and I will share some results in the presentation. Then we got a project through the Global Challenge Research Fund of UK. It was a UK, China, Malaysia project, which was looking basically more into designing electrification schemes that are resilient and sustainable to withstand extreme events. Then in 2020, we got the first project led by industrial partner in UK looking on resilience. And then we also had a project with the US Department of Defense, the Army Corps, in collaboration with different universities in the States. And very recently, we were awarded 3 new Horizon Europe projects looking into this topic. So it's going to be a very busy as well as exciting period moving forward in the next 3-4 years on the topic. So resilience is not, because there was a bit the topic of discussion when it comes to power systems on the concept of resilience. In general, resilience is not a recent concept. The first reference to resilience was back in 1818, okay, in a quite different discipline in timber. But it was defined, it was referred and defined as a concept almost like in two centuries ago. And also from the 1990s, there were efforts from the United States and so on to assess the physical vulnerability of electric system to natural disasters, sabotage, and other threats to electrical power systems. Anamika, I can hear a bit of background noise. I think it's coming from Janine.
Yeah, trying to mute.
Okay. Thank you.
Thanks.
Thank you. However, we see a big increase in the work on the topic on power system, power network resilience, or resiliency, as you call it in the States, in the last decade or so. And the reason for this are many, as there have been rapid changes and stresses in the energy landscape with the introduction of intermittent renewable sources, the increasing reliance on reliable and resilient electricity for the electrification of heating, transportation, and so on, which leads also to increasing and complex interdependence between critical infrastructures. And let's not forget the threats and the shocks to electricity infrastructure, such as, for example, windstorms, floods, earthquakes, wildfires, and so on, which really put resilience in the spotlight of power system planners, operators, and decision-making bodies. But when it comes to high impact, low probability event, I mean, what is really a HILP event? I found this example online, which I found very interesting, which was basically from the outskirts I think it was in Manchester, when a lovely bull that we can see in the photo had an itching bottom, who decided basically to scratch on a transformer in a distribution network in a village in UK. It knocked down the transformer, and then basically it led to a small power cut to 800 homes, which were restored very quickly. And the bull is safe, no electroshock, so everything was fine. So one might claim that this is a HILP event. But we ran a survey within the CIGRE working group that I was chairing since 2017. We ran a survey among 100 responders around the globe on what HILP events they're basically facing in their own system. And this is the responses that we got, which includes basically all the basic events, all the known events, let's say, such as wildfires, floods, cyber attacks, seismic events, and so on. But very interestingly, about 1/5 of the responder also responded with pandemic. So, and this survey was done in 2018, was way before COVID. So none, and when I say none of the working group members paid attention to that cause, to the pandemic. Which, as we evidence later on with COVID, had a huge impact. So basically, we don't know if this was from experience in their own network, it was an epiphany, or it was a back to the future moment from the guys that actually responded with the pandemic as a HILP event for power systems. So there have been very recent blackouts around the globe, which bad weather contributed and attributed to some extent to the blackouts, which, for example, the South Australian blackout in 2016, the UK blackout in 2019, also the very well-known Texas blackout in 2021. And let's not also forget about the near misses. I mean, the near misses sometimes, because they have not led to any tangible impacts, consequences, sometimes they're ignored. But this particular event, for example, in 2021, in July 2021, there was a fire in basically the borders with Spain, in the south of France, which threatened basically the power system. There was a big frequency oscillation with some low disconnection. And if it wasn't for the fast frequency response from the Spanish system, we could have been talking about a new system separation, basically, of the continental European network. So these problems are known, and they have been known for some time. However, there are some limitations in the current regulatory standards when it comes to planning and designing the system and operating the system to withstand the impact and quickly recover from these events. And this is just an example from Ofgem. Ofgem is the electricity and gas regulator in UK, where basically, as we can see in the slide, so basically the target for national grid about the annual average energy not supplied was 316 megawatt hours in the previous regulatory framework, which was reduced to 147 megawatt hours in the current regulatory framework. So we see that basically Ofgem is tightening the security requirements for national grid a lot in order to increase basically the reliability of the system. But this indicator refers to average energy not supplied during a year. And then basically, if you exceed that limit, you are penalized. If you remain under this limit, you are being rewarded for maintaining the safety and the reliability of the network. But we see, I mean, from this figure that there have been quite a few events that exceeded basically this threshold. And also the blackout in 2019 resulted to over 1 gigawatt of load shedding. So we can see that using the average energy not supplied hints a risk of neglecting and not properly basically designing the system and giving the initiatives and the incentives for resilience-driven planning to withstand this kind of extreme events. And if we do an analysis, we did an analysis, sorry, of UK outage data. And although basically the number of power cuts because of weather counts only for about 2% in UK, the customers per power cut though for weather, it's huge. So the weather has a huge impact in UK, worldwide, and it should be included basically in the regulatory standards in order to incentivizing the resilience-driven investments. And this is a nice figure that I like when it comes to basically showing in a more graphical, funny way the problem with going with average indices for resilience of applications, which basically shows a statistician that was trying to cross a river that was on average only 3 feet deep, but there was a point in the river that was much deeper than 3 feet and basically drowned. So this shows the risk of using average values for this kind of risk-based applications for resilience. So if we see this in a more mathematical formulation, let's say, if we consider this probability distribution for ENS, so in the y-axis we have the probability, in the x-axis we have the energy not supplied, and we have this probability distribution. So currently what we do, we drive and we design the system, we plan the system based on credible outages, based basically on the mean, on the average, or on the expected energy not supplied. This is how we traditionally design the system for decades. Undoubtedly, I mean, power system is perhaps the most reliable critical infrastructure that we have. But these tail risk events, such as natural hazards, extreme weather, catastrophic events, common mode failures, which actually lie in the tail of this probability distribution as high impact, so high energy not supplied, but low probability, and become more and more frequent. So a lot of people say that this will become the new norm, as we evidence, for example, in Florida, that they suffer from a hurricane every year. In Europe, we have wildfires every year. In Chile, they have earthquakes, a lot of earthquakes, I mean, hundreds of earthquakes per year. So these kind of events are becoming more and more frequent and more disastrous because of climate change. Let's say, lots of people don't believe that, but let's ignore that. So because of climate change, lots of these events are becoming more and more frequent, longer, and more impactful for the network. So we need to do something about it. There was a reaction by many organizations in the last years, including, for example, the National Infrastructure Commission in UK 2020, where basically urged Ofgem, the UK regulator, to come up with new standards, new resilience standards, which should be overseen by the regulators during regular stress testing of the system. And there was a reaction by the UK government to this report, which was out in September 2021. And they promised to publish what they called the resilience strategy. That was not published yet. It was supposed to be published like a year ago. We're still waiting. But this basically resilience strategy will set the guidelines for network operators and network owners to explicitly consider resilience as a planning criterion. So what is it? We talked about a lot about resilience, but what is really resilience? Within the CIGRE working group that we've been working on for the last years, we simply defined resilience as the ability to limit the extent, severity, and duration of system degradation following an extreme event. And there are many features, there are many key features that basically need to be taken into consideration when we talk about resilience, such as the anticipation, preparation, and so on, which are very well known from other definitions as well. But within our definition, we also put another feature, which is the sustainment of critical system operation. So basically, within the CIGRE working group, we kind of acknowledged that when you are exposed to a HIP event, to a high impact low probability event, it's almost impossible not to lose some functionality of the system. So what this feature basically says is to maintain basically a minimum system load level in order to maintain a reduced but acceptable functioning of everyday life. So basically you secure the functioning of people's modern everyday life, and then you try to recover as quickly as possible following that maintenance of a minimum level of security and electricity supply in your system. And we published some papers and some blog articles on this definition if you would like to find out more information. So following this introduction, which I hope was not too tiring, to go into more technical discussion now on different tools that we developed. So the first tool that I would like to mention is what we call Resilient, which basically a realistic event simulator for international location independent edge network testing. So as you can see in this GIF that we see here, this is Hurricane Matthew, which happened in 2016 over Florida. So basically the model we developed is a fully flexible and modular simulator. And when I say modular, it's built in a way that the end user can use specific modules, specific functions of the simulator that it is to their interest. It's very flexible as it enables the user to define several critical features, such as the number of hazards per year, the temporal and spatial modeling, how long it will last, where it will move, the intensity of the hazard, and so on. And it can also simulate random events in a stochastic manner, as well as simulate historical events as the one we see in this GIF, which is basically the Hurricane Matthew back in 2016 in Florida. So we see in this GIF that as the event moves across the network, what the simulator does basically, it identifies the assets that are affected by the event and the intensity that the assets are affected by the event. So it's a very nice model we developed. We applied this in many parts of the world with quite positive feedback so far on the model. And so basically what is also coupled to this event is what we call fragility-driven analysis, where we see in the bottom left figure what we call the fragility curve, which basically relates the probability failure of an asset to the wind speed that is exposed to. Then it can basically derive the time and the hazard-dependent failure probability and status of the assets, and then calculate the energy not supplied due to the event in a spatial temporal manner. It can output a lot of results, as we'll see in the coming slides. So a version of that model has been applied also in the Project Forward resilience measures that we run with National Grid, the consultancy company Arup in UK, which was shortlisted for the Consultancy and Engineering Awards in 2022. Unfortunately, we're just runner-ups. We didn't win the award, but even being shortlisted was a huge achievement among tens of applications. So within this project, we developed a resilience tiered approach. So in tier 1, what we did basically, what Arup led in the project, was a more, let's say, a qualitative study for understanding the maturity level of National Grid as a business, as an organization. So it was more into the internal mechanism of National Grid towards responding to an extreme event. And then in the middle, in tier 2, we basically try to link the project to existing and planned initiatives to actually see what needs to be changed, what needs to be improved, if you like, in existing practices of National Grid in order to take resilience into account. In tier 3 is what we led in the project, which basically the quantitative resilience assessment tool, which as I'll show later on, we try to basically assess the impact of physical shocks and network stresses on National Grid's network. So this is just an illustration of this hazard simulator that we had. So basically, we modeled different wind speed events with floods across the system. And these figures basically show the capability of the simulator to actually identify the intersection of the lines that are affected, to output that to the system operator so they know in close to real time which parts of the network are affected and by how much, for example, how much wind speed they are exposed to. So it's a very nice tool for visualizing and for identifying basically the vulnerable areas of your network. So within the project, what we did, and just to mention that this is for demonstration only, so we basically had a version of the results with the full network and a version of the results that we can share with people on a simplified version of the network, and just for confidentiality reasons. So we developed what we call the network stress testing approach in order to identify the breaking point of the system. So what we did, we simulated thousands of scenarios with different spatial, different temporal resolution across different parts of the networks just to see which is the point that national grid starts seeing some load disconnected. And we basically identified that this is around 40 meters per second. And then basically we identified this as, if you like, what we call the breaking point of national grid, which basically what it tells to national grid is that beyond this point, when you are exposed, you should or you would expect to have some issues in your system operation. You might see some load being disconnected. So basically, this is the range that you should be designing the system for in order to withstand these kind of events. And we can estimate basically the energy not supplied per windstorm, the CVAR indicator, which, as we said earlier, is basically the conditional value of ENS focusing on the 5% more extreme events. And then also on the right-hand figure, we can see the spatial resolution of the energy not supplied across England and Wales. What we also did, just to examine the sensitivity of our model to different inputs and different assumptions, we tried to make the infrastructure more robust by shifting the fragility curve more to the right. So when we shift the fragility curve to the right, we basically make the assets stronger against higher wind speeds. So as we expected, the breaking point was moving more and more to the right, so to higher wind speeds. But there was a point between 15 and 20% of increase of the robustness of the network, where basically we didn't see much increase in terms of the breaking point of the network. So basically, what we're saying is that beyond this point, however robust you make the network, based on the money that you spend, you will not see a significant increase in the robustness of your network. And we evaluated the impact of this network robustness as well to the conditional value at risk and the expected energy not supplied, just to give an idea to National Grid when it comes to when you choose different investments, how your average energy supplied in your conditional, the more risk-based values of your energy supply change when you invest to more and more infrastructure. And we also evaluate the resilience of future energy scenarios. So National Grid, in their future energy scenarios documents, they have a lot of potential futures that National Grid might see, and with the penetration of heat pumps, electric vehicles, and so on and so forth. So they were interested basically in applying our models to see how those future energy scenarios behave in terms of when they're exposed to a severe, let's say, windstorm. And we provided basically these findings to National Grid to show them how the different scenarios will behave in terms of resilience in the future. And we also defined and designed, this kind of more friendly, if you like, web interface, where basically the National Grid engineers can play with different scenarios. They can see in real time different outputs. So it gives them an idea in a more visualized, friendly way on these resilience outputs from our tools. So far, what the work with National Grid was more, let's say, a static analysis. So we were modeling the windstorm, we're seeing which assets will fail, but we're not modeling the cascading across the system. This is something that we are doing now with National Grid. It basically provides much more significant and meaningful outputs. So what we did with our team in the last couple of years, we developed different cascading models, which basically, when you have the initiating event, let that be n-1, n-2, or n-k, where k basically can be in the order of tens of hundreds of assets failing very close to each other. So we developed this AC cascading model for resilience application, which includes the modeling of different protection mechanisms. And as we see in this illustrative figure here, it can generate and can visualize basically the different steps of the cascading as it propagates across the network. So in this simple illustration, which is the very well-known 39 bus, so we start with the healthy part of the system in the top right corner, Then we have the event, then we have some overlay protection tripping some lines. Then we have the disaggregation of the system to many islands. Some of them survive. Some of them basically are blacked out, which are shown by the red dots here. And then basically it shows the sequence of the protection operation as we go further and further and further in the cascading. So this is a very nice tool as it provides basically a nice visualization, very nice statistics on which protection mechanisms operated, which is really the biggest problem is if it's a frequency or a voltage problem. And this code is openly and freely available in GitHub. If you would like to download it to see yourself if it works for your purposes. It's a fully documented source code. There are comments across the code, which helps you basically understand very quickly the code. It comes with the examples and everything you need basically for setting the code up. And we also have a very detailed publication on this code, which is very helpful in order to save some time for you when you're familiarizing yourself with the code. So further to that, AC cascading, which was basically modeling the dynamic phenomena, but more in a static way. We also developed a full dynamic cascading failure simulator for renewable rich systems, which basically runs in DigSilent, which is interfaced with Python in MATLAB. So we run the main code from MATLAB to run basically the cascading and so on. And then we run the dynamic stability in DigSilent, which takes quite a lot of time if you want to run a lot of iterations of the cascading. But we got some very promising results, and we have a couple of publications on this as well. And we apply, for example, this an application on the synthetic Texas power system, where we tried basically to see if fast frequency response with this model can support basically can mitigate the impacts of cascadings with increasing wind penetration level. And this is something very important because as the renewables get more and more in the network, as we know, the system inertia is reduced more and more. So basically having fast frequency response services is very important. And this model can actually quantify the contribution, the impacts of cascading first on the dynamic stability of the system, and then the contribution on different services such as FFR on mitigating the impacts of potential cascadings for high penetration of renewable energy sources. And this code is also available in GitHub with all the documentation available if you want to have a look. And we also have a paper which basically walks you through step by step on the Python script basically to help you test and try our model. So if you have any questions on these two models, if you are interested, if you want to download them, if you have any questions, please feel free to get in touch. So I will skip this just for the sake of time. So the next tool that I want to talk about is what we call CIPROS, which basically stands for Capital Investment Planning for Resilience Optimization of Smart Grids. So basically, this is it's a modular tool which has different interesting features. So we have the weather event simulator that we described in the previous part of the presentation. We also added a feature on GIS-based modeling of the energy, the transportation, and the communication system in one platform. So basically, we can optimally coordinate the dispatch of mobile energy resources. And it's very important to consider beyond just the electricity, also the transportation, as well as the communication system in order for optimally coordinating these mobile resources. Based on this, we also offer in one platform a decision-making basically tool for resilience-driven investment portfolios, which can achieve effective trade-offs between profit maximization for the utility as well as risk mitigation. And we're currently working on a graphical user interface in order to make this tool more user-friendly and easy to deploy and easy to use for the end user. So this is just, some figures of the functionalities of the model, which I will explain in more detail in the coming slides. So we can basically project any power system at any part of the network. If it's a test system, if it's a real system, of course, we're using the real system. We have the the event simulator, where basically is what we discussed earlier. We also model, as mentioned, the transportation system, which is basically what we see in here as an example from Portugal. And we can provide customized investment portfolios, which I will talk about in the coming slides. So an example of this planning tool, which basically this work within Chile was a previous version, if you like, of Kypros. So in this work, what we did with the Chilean colleagues, we developed an optimization via simulation model. So basically there are two stages in this work. In the first stage, we basically propose different enhancement options to the system operator through optimizing a resilience metric, whatever that is. It's up to the choice, up to the reference, up to the preference, sorry, of the system operator. Then what we do, we basically throw that enhancement option to the second stage, which is the simulator we talked about earlier, which basically simulates the impact on the system, the response, the restoration, and so on after random natural hazards occur. So we have the base network, then we select basically an enhancement option, and then we quantify the impact of that on the network. And that's an iterative process, subject, of course, to budget constraints, until the optimal portfolios of investments are identified. And in this, what we show basically in this slide, on the top right here in the two tables, we have the rankings when it comes to reliability approach, where we have basically the expected energy not supplied, so the average energy not supplied, which is more reliability driven. And in the, sorry for the messages, and on the right-hand side, we'll have basically the resilience application. So basically, when it comes to the conditional value of the energy not supplied. So we see basically with this ranking that, okay, in the top position, we have the HVDC link, which was built recently in Chile, which basically connects the north with the south part of the system. So it bypasses a lot of the infrastructure. So it's a very attractive solution. When it comes to reliability, as the most well-known reliability approaches, the optimizer basically was biased towards adding more and more infrastructure, so adding more lines. While when it comes to resilience, it was more into hardening the substations, critical substations in the system before you actually go to basically further expand your transmission infrastructure. This is for individual solutions, though. When it comes to looking the solutions as a portfolio, because as we know, when you apply one solution, then the impact of the second, third, and so on solution of the network is actually changed. And because we need to see an investment portfolio as a whole and not as individual solutions and their impact on the network. So basically, what we see here, when we consider the conditional values of energy not supplied, we see that we start with the HVDC link, then it's hardening the substations. But then actually the optimizer does not favor building new lines, but adding more storage in the system. So basically, we're adding the controllability of HVDC link, which is a mean, if you like, of additional flexibility in the transmission network. We also add storage, which adds further flexibility. And we also harden the infrastructure with the substations. So it's a trade-off, if you like, decision between flexibility means and infrastructure hardening actions in order to basically reduce as much as possible the conditional values of energy supplied and hence increase resilience of the Chilean transmission system. We also did another example in Chile looking at wildfires, which we published last year in a special issue of the Power Energy magazine when it comes to the role of distributed energy resources for enhancing system resilience. So in Chile, they suffer a lot for fires. So basically, this is the main corridor of the Chilean transmission network, and this is where the big demand centers lie on the west of the country. So what we did basically, we developed this simple case study where we have the main grid. And then we have two neighboring areas, as in the case of Chile, where basically we had two lines connecting each of the system with the main grid, two lines connecting these areas between them, and then we consider different DERs randomly in the two areas just to evaluate the role of flexibility. So and then we consider that there was a fire, basically as driven by a real event in Chile, that was disconnecting basically these two transmission corridors connecting area B with the main grid. So table 2 here on the right, it shows three cases. Case A is basically when we do not consider wildfires or the impact of wildfires. Case A reevaluated is with the same asset and measures, but considering the impact of wildfires. So we see basically that the load cost increases significantly from 27 to 19.5 thousands of US dollars. And then case B is basically considering the wildfires, but applying a resilience-driven planning and operation of the system, as we've seen in the previous slides. So we see basically that when we do that, we harden the infrastructure, but we put more PV, more batteries, and so on across the system, which of course increases the investment in new PVs and batteries for Chile. But at the same time, we managed to reduce a lot the lost load cost, and also the operational cost. So we basically balance the investment costs with the savings that you get when you get an extreme event. And the total cost is actually approximately the same as the case with not considering the impact of wildfires with a simple N-1 case study. So the next tool that we developed very recently is called the MERS-DEEP, which basically it's a mobile energy resource scheduling and dispatch incorporated in optimal power flow models. So as we see in this figure, and as I said earlier, this is a multi-layer platform. So it has the electricity system, it has a transportation system using Google Maps, basically using Python API. So what we're trying to do here is to take into account the driving distance of the mobile energy resources to reach a point in the network. In many existing works that we've seen in the literature, they just assume the electricity network and depot of the mobile resources, and then they assume that they are dispatched randomly in different nodes. But what we actually do in this work, we actually consider the driving distance between the depot of the mobile energy resources to the affected network, and if the transportation system is affected, which neighboring depot can actually dispatch the mobile energy resources to the affected part of the network, in order to basically take into account in one single platform the status of the electricity network as well as the transportation. And this is just a graphical illustration of basically a mobile battery moving to a node in the system, which here in this work we prioritize the minimization of the critical load not served. So we see here basically that we achieved to minimize a lot the critical load not served. We lost some non-critical load, but that is something that we can live with when we have an extreme event. So this is a very nice simulator in order to co-simulate and co-optimize, if you like, the usage of the electricity and the transportation network. We did this based on reliability as well as resilience-centric analysis to see the impact of having one MER or multiple mobile energy resources dispatching across the network. So what we also did, very briefly, we also developed different machine learning approaches under deep uncertainty when it comes to operational decision making. And this is just an illustrative example here where we basically consider the option of islanding as a mitigation measures against cascadings. Because when an event approaches, we don't know where exactly it's going to hit, by how much the network will be affected, so on. So what we did, we trained a machine learning algorithm with hundreds of thousands of cascading events on different locations of the event. So when the actual event happens, we just use some simple characteristics of the event to throw into these machine learning algorithms to give basically in close to real time the optimal solution for operational planning, for basically splitting here the network into different number of islands. So another case study that we did in the project with Malaysia. So we're tasked basically by Sarawak Energy, which is basically the electricity distribution operator in Borneo Island in Malaysia. So basically there are a lot of location of villages which are rural, which are basically very remotely located in Borneo Island. So Sarawak Energy was interested to see if it's better to basically expand the existing grid to reach these villages or to use an off-grid electrification through what they called Sarawak Alternative Rural Electrification Scheme, which mainly is batteries with PVs installed in different villages. So this is the total cost comparison between on-grid electrification and the SARA scheme that we did the analysis for Sarawak Energy, where we see basically that in most of the cases, SARA's off-grid solution is much cheaper. But there is a caveat here because the rural areas in Malaysia that are significantly affected by floods and by landslides. So we should take into account basically these events when we want to propose, if you like, the better solution for Sarawak Energy. So basically we have different events here with different probability, different occurrence, different consequences. So we have different scenarios which we propose to Sarawak Energy for basically have access following existing roads, which is the easy way, and then avoiding areas with moderate high risk of landslides, of flooding, and combined impact of those hazards. So this we see in this diagram basically the flood risk, the landslide basically risk, and then different solutions that we provided for basically having off-grid solutions and then interconnecting as well the off-grid villages between them in Borneo Island. We also did some work on cyber physical risk assessment in collaboration with the Department of Defense, Johns Hopkins, University of Pittsburgh, Colorado State University in the States. So where one of the case studies was the island of Oahu in Hawaii, where we basically try to see the increasing risk when we're considering the coupling of power communication systems with and without the mobile energy sources that we've talked about earlier in the presentation. And as we expected, basically, the more interdependencies we consider, the higher the risk of cascading impacts and power disruptions is for the island. But we're able basically to quantify the impact of hurricanes on the island with and without considering the coupling of the power communication infrastructure. We provided very useful insights for the local authorities there to better organize and plan their system. We also recently started doing some work on multi-energy resilience, which is becoming more and more important with the conflict of different energy vectors, for example, electricity, gas, heat, and so on. And we're trying now to understand how a failure in one system can propagate to other energy sectors, energy vectors, sorry, and how in a whole multi-energy system we can basically leverage the flexibility from different energy resources in order to better withstand the extreme events. And just to a final slide, and just to close my presentation, something that I'm personally quite pleased with and proud, if you like. So there is an initiative and everybody can join. If you want to join, you can find the details in this link, which is called Bridge Ukraine, which is basically a group of academics in a volunteer manner that we try to develop tools in collaboration with Ukraine authorities to see how can basically support Ukraine's post-war recovery when it comes to critical infrastructures. So this was our first publication on the topic with very excellent and very well-known colleagues. And we're trying basically to enhance our links with the Ukraine authorities, which were very open in order to get support how to recover basically from the unfortunate event of the war in the country. So again, we're very proud of this work because we're hoping to do a real impact for the country. If you are interested in joining, please get in touch. That will let you know how to basically get in touch with the chair of this initiative to join us. So the tools that we developed, we're hoping to make them open source because they're developing to European projects, which supports and initiates, and motivates, encourages making the tools open source. So hopefully later in the year, this will become available and free to use for everybody. And as I mentioned, we have the New Horizon Europe projects. So we hope to have more and more updates in the coming years on the topic. And just some acknowledgement on different projects, some further reading for you if you like to read more about our work. So thank you very much, Anamika. I hope I didn't exceed my time too much.
That was perfect. Thanks, Matthias, for very interesting presentation. It was great to learn about the different aspects of your work and different, um, ongoing and past, results that you have for this cross-infrastructure resiliency along with the grid resiliency portions of the work. So we're going to open it up for Q&A. Um, let's see, if you have any questions and you're online, just raise your hand and I can call you. We'll start with questions with students. You can unmute yourself and start asking questions. All right, I see folks being quiet. So let me start with first question. So, but I was very interested to see some, discussions you had around weather event modeling that you were integrating with these, impact analysis. And you talked a lot about also on the flood modeling as well as, wind storm modeling. How are you integrating these, weather modelers or the data through that on the grid impact side? Basically, what is the source of data that you are incorporating, or are these models that you are developing?
Yeah. So basically, when it comes to, I mean, we in the let me go back for a second. So for the Portuguese at least case that we have in a European project, there is a database that we can download a lot of historical events that actually happened across different parts, and there's also some relevant information for other parts of the country. I can send you the link, and including United States. So basically, what we did, we downloaded as much as information we could find from those links. And then we try to train our simulator basically and fine tune the parameters of our simulators based on those events. So including the trajectory of the event, the intensity, the duration, and so on. So where possible, we used real data to actually train the simulator. But after that, because as you know, I mean, this is random. These are random events. We basically define the range of the different parameters based on the historical events to let the simulator create stochastic and random events.
It makes sense. Sorry. Uh, okay.
There is a question from
Yeah.
Sajif.
Yeah, so just let me complete the thought once, and Sanjeev, I'll call you. Just give me a second. So Mehta, just to further maybe stretch a little bit on that point. So let's say that you want to simulate the flood for the region. I mean, do you have like rainfall data available and the storm surge data available, and you kind of map it for those particular events, and then you randomize them to create? Is that the correct understanding on how you end up simulating those
Yes,
places?
yes,
Okay,
that's exactly,
okay,
yes. I mean, when it comes to United to the UK studies, what we did, we collaborated closely with the Met Office in the United Kingdom. So they share precipitation data with us.
okay,
And then what we did, we basically took those data and we went to National Grid. And we sat together with them to try to understand basically what was the risk of flooding and
okay.
what actually floods happen for those events. And then we try to basically fine tune again our models to match as closely as possible the events that happened. But when it comes to the last studies that I've shown for Malaysia, actually those models, these models here, I mean the flood models that we have for Malaysia here, those are very detailed models because they were developed by climate weather modelists from Newcastle University that we had the project with. And these models, I mean, I need to be honest, they are far more advanced of the models that at least me and my team can develop.
Sure.
Because they took into account the return periods, mirror analysis data, and so on and so forth in order to train their flood models. So there are very detailed models, and that's, I think, an issue that we need to solve from our energy community, at least side, to communicate more with these people.
Yep.
Because they have the models, they have the data, definitely much better data and models than we have. But I think, in my opinion, we don't communicate enough.
I concur. I'll pause for a while and maybe let Sanjeev, you had a question, and then I'll come back to if I have some time to ask a couple of more questions.
Yeah, thank you, Pranamka. So thanks, Matheus. I think it's glad to see you virtually presenting here. I've gone through your papers and the CIGRE report as well earlier. So a pleasure to see your work again here. So I have one question. I mean, a couple of questions, but I just started into one question. So the major thing is like, how do you really consider these the probability of losing one of the assets when you don't really have an access to the physical strength of those assets? Like you just map it with respect to the wind speed, like the wind gust is the one of the probability that you took it. So how do you really map it? Because nowadays what I've seen in from the industry is they're projecting towards the digital twin that maps to all these structures, starting from civil, mechanical, all those structures. So that's what the digital twin now the industry is moving towards. So, but there, the elevation, everything will be accessible. The flood and even the wind gusts and the strength of the poles, everything is visible to them, and based on that, they're deciding. But in your simulation, how did you consider those parameters when you do the analysis for it?
Yeah, Sanjeev, I mean, that's a very, very good question. And that's, I said earlier, I'm always honest, transparent with our work. So that's a limitation indeed of our work, Sanjeev. I admit it in many venues. I don't mind. I mean, the fragility model of how, I mean, what we do, we use as many scholars coming from the energy power system community, we use the concept of fragility curves to relate basically the failure probability of the assets to the intensity of the hazard. Now, those fragility curves, some of them were developed based on, let's say, experiences. Others were developed based on real events, if there were data, if there were enough data actually draw some statistical analysis out of those data. But there is an uncertainty around that. And that is basically what we identified as a big limitation in our work, and what is currently we're working on, and we're hoping to be successful in another round that we did with National Grid now. We tried to do that in the previous projects, because as you very correctly said, the National Grid engineer said, okay, you are using a fragility curve, but an asset being, for example, on the coast, exposed to winds, is in a much worse situation than an asset being in mainland. So the asset health index is different, the aging is different. So there are a lot of parameters to consider when it comes to basically characterizing the fragility and the vulnerability of an asset. That is something that we hope to work on and to improve in our future work, Sanjeev. But that was an excellent point. If you have any recommendations, I would be happy to follow up with you to discuss it further.
Yeah, sure. I'll follow up offline on those ones. So we did similar work with Professor Anurag here. So you're continuing it. The last question again, your tools you developed it. So are they reactive enough? Reactive, I mean, like, would we able to modify any parameters to just load our own system, and then could able to analyze the any system? Are they very reactive in online or offline, even if it get pulled from?
Yeah. I mean, the tools, I mean, it's so you're talking about the cascading simulators.
Yes.
That are already available. Yes. So this one, the first one has already been used by many colleagues of mine, and we got very positive feedback. So it's very easy to, I mean, very easy. Okay, you need some time, but an average familiarization time that we got from colleagues was basically 2-3 weeks. You are up and running with the model. And then basically you can put in any network you want. I mean, it has clear instruction how to do it. And it's basically using a math power case studies. So if you have a network in a math power format, basically, I mean, this is very straightforward to run. When it comes to the dynamic model, a nice feature that I forgot to mention is that basically it can automatically develop the dynamic network, the dynamic, the dynamic parameters of any network. So it can basically define the generator parameters, the line parameters, so on in the dynamic data for any network. So that's another nice feature. So you can put in any network you want. I mean, the code will develop the dynamic version of that network based on some assumptions we have in the model. And then you can run the dynamic studies. I mean, this is a bit heavier than the other model because I run a full dynamic study. But they are quite user-friendly, yes.
Oh, thank you, appreciate it. Yeah, thank you.
Thanks, Sanjeev. Back to students. Any questions? Okay, go ahead.
Can you go to your maybe second or third slide in which there was a graph?
No.
I mean, I don't have a question. Just come here and let's talk.
Okay. Oh, is this the?
So where?
There was a graph which was showing reward and penalty.
Here.
Yeah, so very simple question. So what is the form of this penalty or a reward? Is it monetary or
Yeah, it's monetary.
regulator imposed? Could you go a little bit more on it?
So basically, I mean, the penalty is monetary. I mean, they have to pay a penalty, which is basically depending on how much they exceeded. The reward, it really depends. It might be a further incentive, financial incentive to basically build more infrastructure or relaxation of the amount of penalty they have to pay in the next basically violation. So the reward varies depending on the application and from the regulator.
Okay.
Other questions?
Yeah, I have a question. Actually, you talked about dynamic stability. What kind of stability you have considered in your study? Angular, voltage, or frequency?
Voltage and frequency, yeah.
Voltage and frequency. Also, I have another question. Why did you club n-1 is a static study and stability is dynamic simulation? So why did you club these two different studies together?
Why did we do what? Sorry?
No, I want to understand that why did you include n-1 contingency in your stability study?
Why we included -1 in the
Yeah,
stability study?
n-k in your stability study.
Yes, so the n-k, basically when you have an extreme event, so we know the n-1 and -2 study. So you lose one asset or you lose two assets at the same time. And then you basically do the security assessment against those events. So when we say n-k, what we mean basically is that k, which shows the number of outages when it comes to high impact low probability event, can be significantly bigger than 2. As we evidence with earthquakes, with hurricanes, a big part of the infrastructure can fail in a very small amount of time. So the n-k, which basically our simulators can go up to n-hundreds of assets as an initiating event, is basically exactly to model this bigger impact, if you like, of a HIP event when it comes to affecting and losing in a very short period of time a large number of assets.
Yeah, but that is a static study, right? How do we include that in a dynamic simulation?
We include that as an initiating event.
Oh, okay, as an initiating event. Okay.
Yes.
Okay, thank you.
Yeah.
All right. Thanks, students. So, Matthias, maybe maybe some comments from you. I would like to hear what will given all the research that you have done in collaboration with getting all the data with all the relevant stakeholders from industry. What suggestion you have for power systems researchers working in the area of grid resiliency? What is like key takeaway that you want us to think about as we are delving in, this highly interdisciplinary domain?
Yeah, Amika, to be honest with you, the main message that I have basically is that we need to work more together. Because the more and more we're getting into this topic, the more and more we realize that we cannot do it ourselves as energy engineers. As you are saying in your project that you have now, we cannot do it alone. We need to work more with other disciplines, including climate, weather modelers, and even other critical infrastructure. Water systems, transportation, communication, and so on. When it comes to data, and which is a big topic of discussion, as you very well know in different conferences and so on, I wish to see system operators sharing more and more data and experiences with this. In Europe, there is a trend, and we're trying to push towards that through the different projects we have. But we still have a long way to go in terms of getting, if you like, satisfactory, reliable data, because with the experiences, unfortunately, we're having in the last 20, 30 years, people say there's not enough data, but there is. There is enough data, it's not shared. And that's the problem, at least in my opinion.
That's an excellent point. Okay, let's thank our speaker for today, everyone. Thank you so much for a very interesting talk. And
I hope it wasn't very tiring. I tried, Anamika, in the time I had to give you a broad, idea of what we're doing. And as I said, I would be very, very happy to follow up with any of you guys if you have any thoughts.
Thank you so much. And yeah, it was very, very interesting and engaging. So thanks so much for that. And with that, we'll close today's session. Thank you everyone for attending. And thanks, Dr. Panteli, for exciting seminar. Have a great
Thank you very much.
day
Thank you
and
all.
good night to you. Thank you.
Thank you. Thank you. Bye bye.
Thank you.
Thank you all.